We're asked to find the conjugate base of sulfuric acid. Well, first of all, what is a conjugate base? In a Bronsted-Lowry acid-base reaction, our acid, which we will demonstrate with H2O, will actually depronate, and depronate means just to strip off a hydrogen to give us another molecule, right? So notice that the water donated a hydrogen, so it's our acid, because in an acid-base reaction typically we're working with hydrogens, except with Lewis acids and bases. So the base can actually accept another hydrogen to become the acid again, right? By the way, the difference between a Lewis base, and a Bronsted-Lowry acid and Bronsted-Lowry base is that for Lewis acids, they only deal with electrons. For instance, Lewis acids they love electrons, so they're going to be accepting electrons. Lewis bases, however, they don't like electrons, right? And so they donate electrons. Compared to this type of reaction, you only have hydrogens, and the other one you don't deal with hydrogens. That's the only difference, really. Right. So why does this occur? Well, in the water molecule, you have some hydrogens and an oxygen with two lone pairs. Oxygen is more electronegative, therefore it's gonna, whenever this reaction occurs, the electrons that break from this bond go to oxygen, because oxygen is more electronegative. It's going to have like a magnet, an affinity towards electrons, so it's going to pull it towards it. And we will get the hydroxide. We're going to put our original lone pairs right here, and we will show our new lone pair that we got from the oxygen, or from the hydrogen. And we will have the hydrogen. So hydrogen is like a proton, it's always positively charged, right? But you got to notice something very important, that typically in the acid-base reaction, you're going to have a negative product, right? Notice that we went from a neutral to a negative. So typically, in acid-base reaction, you will have a negative product, right? Alright, so since we now know what to look for, we're going to look for a negative sign. This is a positive sign, not good, right? Not good. This is neutral, not good. This has a negative sign, that's good. This is neutral, that's bad. And this is negative, that's good. So now it's the difference between HSO4 and HSO3. I'm going to assume that it's been a minute since you've taken general chemistry and you forgot your acid formulas. So I'm going to show you a trend. The trend is, for most molecules, the more oxygen you have, the more electronegative you will be. And the more electronegative you become, the more acidic you are. So the more oxygens you have, the more acidic you are, right? Okay. This only occurs for specific molecules. It does not occur when you have phosphorus. So phosphorus acid, not good. It's actually when you have less oxygen, you become more acidic. So for phosphorus only, it's not going to hold. But for the most part, for most of organic chemistry, the more oxygens you have, the more acidic you'll be. So knowing that, O4 has more oxygens than O3. So this is bad. And therefore, this molecule with a negative charge and more oxygens is a pretty good candidate for our answer. Which one of these molecules is not a Bronsted-Lowry acid? Alright, so if it's not a Bronsted-Lowry acid, then we're going to be looking for a base. Okay? You should know that water is an acid and a base. It's an acid and a base. It could be both, right? Since we're now looking for an acid, and this can be an acid, we're going to say that this is incorrect. We will skip B. We will go into NH4 because I want to show you an example with B later on. So NH4 has this, right? Okay. And if you were to do formal charge, it would be a positive one on the end. And nitrogen is pretty happy. Nitrogen has all its octet filled, and that's what you want. So we can actually deprotonate. We can take off the hydrogen. We can do this because typically in acids, they have their octet filled, except for water. That one's kind of a weird person. So when you're looking for acids, you're going to be looking for a filled octet. 2, 4, 6, 8. Nitrogen is filled, and therefore we can actually deprotonate to give us H right here, and an H, and an H. This lone pair is going to go back to nitrogen, right? And therefore we can accept something. We can accept like a hydrogen again, right? It could go back here. So it's like playing Legos, right? You want the full. Well, it's not like playing Legos. Here's a better analogy. It's like playing with Mr. Potato Head. You want a Mr. Potato Head that has the full set, right? You're not going to buy one off of eBay that has like 2 arms but no legs, right? You want the full Mr. Potato Head set. So whenever you take off an arm, you could put a nose in the socket, or you could put it anywhere on the potato. So acids and bases are like Mr. Potato Heads. We can take off a hydrogen, we have a lone pair, and then CH3 could come out. A CH3 could come out of here and go here to bond with us. That'd be cool, right? So it's like Mr. Potato Head. What I'm trying to say is you want a filled electron shell for your central atom. Since this nitrogen is filled, it's an acid, so we don't want that. Alright, we're going to go to CH3, this one, we're going to go to CH3CO2H. Okay, so we have our hydrogens right here. Okay, we double bonded to an oxygen. I did this because carbon wants 4 bonds. Okay, notice that my carbon is going to be the central atom, right? It has a filled octet, 2, 4, 6, 8. If you were to take this hydrogen away, you would have kind of like a negative right here, and this is pretty acidic, right? This is pretty acidic. This it has resonance right here. This is a carboxylic acid derivative, and it would be really acidic. But just notice what I did. Since we have a filled octet around carbon, we can afford to do Mr. Potato Head again. We can take off this bond and put it on the oxygen, so it could become negative, right? So that's not going to work for us because that's an oxygen, or that's an acid, and we don't want that. We want bases. So that's not good. It's bad. All right. Now HCCH. H with a C, triple bond, C with an H. Notice that my carbons have a filled octet, and so does hydrogen. Therefore, we can actually break this apart and get HC. This. Oop. Right. And then we could play Mr. Potato Head, put that back where it came from, right? And that's because it had a filled octet. But what about B? Well, CH3 with 3 of them, so this means that we have 3 of these connected to that. Okay, so we have a nitrogen, we have 3 things connected to us. Turns out to be CH3, and you can probably see the problem already. Well, my hydrogens are really bad looking. That's okay. Well, forget about the carbons because the carbons are filled. Okay? But we're going to be looking at our central atom, which is nitrogen. The formal charge for this nitrogen is what? Nitrogen typically has 5 electrons in its valence shell. Okay? So let's count. We have 2, 4, 6. We want 8 electrons, so we're just going to put 2 of them. 5 valence electrons minus 2 electrons is 3, and 3 minus 3 is neutral. 3 bonds, right? So we have a neutral molecule. So what's the problem? The problem is that we have electrons right here. we can play Mr. Potato Head. Okay? We can play Mr. Potato Head because this is a base. We're not going to give up any hydrogens. We want something to come to us. So we can have a CH3, and it can actually merge with us. So because I could play Mr. Potato Head, that's a base, because that toy is pretty basic. It's like everybody has that toy. It's like $10, right? So yeah, it's basic. We don't have a filled octet. We can accept something, right? If we can accept a hydrogen, then it's a base. If you cannot accept a hydrogen, but you can give a hydrogen, then it's an acid. So this is not acting as an acid because we cannot give hydrogens from the central molecule or atom. We can actually get some hydrogens, all right? So we can receive something that makes us an acid or a base, right? Cool. All right. So which one of these molecules is acting as a Lewis base? Right. So in this reaction, what are the the Bronsted-Lowry bases? A simple way to do this is to actually look for your acids. Your acid donates a hydrogen. So we have HA reacts, and well, let's see, plus B is going to react, and you will have A minus plus HB. Right. In this case, since we donated, or when we compare HA with our A again, we notice that we got rid of a hydrogen. Something that gets rid of a hydrogen is an acid. So that's acting as my acid because ultimately we lost a hydrogen. And something that receives the hydrogen is a base. And therefore the acid right here, this would be the acid, right? But it's actually the conjugate base. Because you can receive something, that's what bases do, and then you could become the acid again, right? And similarly, the base in this case would be a conjugate acid, because then we can actually donate a hydrogen, because that's what acids do. And if we donate a hydrogen, we can become the base once again. Alright, so using that kind of step-by-step logic, we're going to find out what donated the hydrogen. Okay, well, if I'm looking for my acid, PO4 3 negative doesn't even have a hydrogen. Water became hydroxide. It lost a hydrogen. So therefore it's an acid, right? If this is looking for Lowry bases, then if we're looking for Lowry acids and bases, then we're going to be looking for hydrogens. This one did not have a hydrogen to begin with, so it's not going to be your acid. This would be your acid, okay? Therefore, if this is your acid, this would be your base, okay? So now let's look now. If this is your base right here, then on the opposite side, it's going to be the conjugate acid. That's always going to happen. If this is your acid right here, then this will be your conjugate base. Always going to happen. It's going to like flip-flop on the other side. Therefore, without even looking at the the answer choices, you can look for bases. So we're looking for bases. Our base right here would be PO4, 3 negative, comma, what's our other base? Hydroxide. Okay, so now we're going to look for our answer choices. PO4, 3 negative right here, and hydroxide. So that would be the correct answer. Okay? In this question, we're asked to find what would be the product of this reaction. Well, the picture shows that this oxygen is going to react with this hydrogen to make a new bond. You're probably wondering what this means right here. It means what we should expect. So our answer should have that molecule in it, okay? Notice that we have metal, which is a sodium. It's a spectator ion, meaning that it's not going to participate in the reaction, it's just going to be hanging out. So instinctively, I'm just going to draw my sodium atom right there, just hanging out, not reacting. Now, here's a mistake that you could have done. You could have done, oh, this bond is moving, this double bond is moving, I'm just going to move it over here to this side. Well, that's not what it's asking for, right? It's not what it's asking for, because we're actually going to be moving that double bond to that carbon. That's what it means. We're going to be directing that double bond to the carbon. Okay? And a double bond, when it breaks, is just a lone pair. It's just a lone pair. So we're going to do that in red. Right? We're going to follow this reaction first. We will have the oxygen, it's actually over here. So the electrons make a double bond with the oxygen. We will have a carbonyl. The hydrogen is no longer there. Okay, it's no longer there. It's going to be formed with the CH3O. We will have CH3O, and that hydrogen that was here connected with the negative oxygen to make a neutral. And we're going to put in our bonds, right? We're going to put in our bonds. Nothing changed except for the fact that this double bond moved to this carbon. But hey, well, we can't move we can't move hydrogens or atoms, right? Well, we're not moving hydrogens or atoms. We're not moving anything. We're moving electrons. Here's why this works. In the original molecule, you were double bonded, right? Carbon wants 4 bonds. This is 1 bond, 2 bonds, 3 bonds, right? And we have an implied 4th coming from a hydrogen. Okay. In the new one, we will have this one and a lone pair. Okay, it has a lone pair right there. And this is right here. Let's actually erase this so you don't get confused. Right. So what happened? Well, here's what happened. It's still a hydrogen right here. It's still a hydrogen, right? Let's actually blow this image up. We have a carbon connected to a carbon connected to another carbon. This has some lone pairs, and this has hydrogen. Okay, and let's blow this one up right here. There's a carbon with a carbon, double bonded with a carbon. There's a hydrogen, no electrons. Okay, let's see here. Well, this is going to be negative right there. Alright, so in this carbon typically has 4 electrons. So 4 minus 2 is 2. 2 minus 3 is a negative. Alright, let's see here. 2, 4, 6, 8 has a full octet. Alright. But notice something. Notice that this bond can break here and form that electron lone pair. We didn't add any atoms. We're not adding some secret H. We're not adding some fluorine. We're just breaking what was already there. We can break that double bond and move the electrons. It's perfectly legal to do that. We're not adding some foreign atom, some foreign material. Okay? So, in the other answer choices, for instance, answer choice B, you forgot to you neglected the sodium, so you don't have sodium in that, so it's wrong. In answer choice C, you're actually merging too many things with hydrogen. Hydrogen can't double bond. It cannot do that. It can only do a singular bond, so it's incorrect. For answer choice D, you're not moving this bond. You're doing everything else except you have this, which is incorrect. Okay? So, therefore, this reaction right here would be the perfect representation. So, what would be the product of this reaction? Right? So, what would be a product? Notice that we have a metal in the mix. If we have a metal, I know that my metal is going to be a spectator ion, and it's just going to be hanging out, just spectating. Okay? So, we're going to leave that there. So, your answer choice should have a spectator ion. So, this automatically eliminates answer choice B, and that's it, right? So, eliminates answer choice B already. Right? So this is kind of a hassle to draw out. So I'm going to neglect this portion because that portion is not reacting. Why would I bother my time with, drawing it? Okay. So, well, let's do the oxygen right there. with the carbon, and this bond is breaking and is going to be forming that electron group. Okay, so instead of drawing it in pink, we'll do it in black. So oxygen, well, yeah, oxygen has this. This was the old lone pairs. We now have a new lone pair, which is in purple. Okay. And what else happened? Well, we formed a double bond, so we should have a double bond. That hydrogen is actually leaving because this hydrogen is going to mix with it. And because that hydrogen is going to be reacting with this one, we should have an H2. Okay? We should have an H2. Alright? So that's a double bond, right? And nothing else changes. Nothing else changes. Right? Okay. Notice that it looks kind of weird, right? It looks kind of weird. Also, I just noticed that for answer choice A, you have like a negative sign on this oxygen. That should not be there because obviously this oxygen is not reacting. So how can it be negative, right? So that eliminates answer choice A instinctively. Okay. So why doesn't answer choice C work? Why doesn't that work? Well, it doesn't work because, well, how can I say? It doesn't work because you have this molecule, right? You have that molecule, or you have that carbonyl group and this double bond, but you still have the two H's compared, right? You still have the two H's. So how did this hydrogen get another hydrogen? You have three hydrogens now. You're only supposed to have, you have four here, but you're only supposed to have three. 1, 2, and 3. You're telling me that you have 4 of them, and that's not correct. The only thing that would be correct now is answer choice D, which makes sense. The reason that you may have been a bit disturbed is because you didn't see the hydrogens. Of course, these hydrogens are going to be implied as normally, right? So this carbon right here has a double bond, it has a single bond. So 1, 2, 3 bonds, it wants 4 bonds. It's going to have an implied hydrogen still in it. Okay? So that would be the perfect reaction. We were supposed to have respect to the ion not interacting. We're supposed to have the H2, and one H made that, so we only have one H right here. This is going to be implied, like invisible, right? This oxygen does not change charges, okay? And just look out for those silly mistakes that the professor could give you. Which one of these molecules is a Lewis acid? What is a Lewis acid? A Lewis acid, which we'll denote as La, is it's an electron. Let's just put electron as negative E, acceptor. Okay. So an acid is an acceptor, and then Lewis base is going to be an E donor. Like the Salvation Army is like a base for the needy, right? And so the Salvation Army donates a lot, right? It donates a lot of what it has. So we're going to be looking for Lewis acids. A main thing that you should look out for Lewis bases is an excess amount of electrons. So it's better to look for a base first to see what you don't have. So we're going to be looking for bases to kind of wean out the competition. Okay, so let's do nitrogen and fluorine first. So nitrogen, you have some fluorine. Okay. So 2, 4, 6, nitrogen typically wants 8 electrons. So 2, 4, 6, 8. Right. Okay. And let's see the former charge. 5 minus 2 is 3, and 3 minus 3 is neutral. Okay, so that's neutral. Is this a Lewis acid or a base? It cannot be an acid because it would be violating the octet rule. If we had some lone pairs coming in, then then you would have some Lewis, you would have some excess amount of electrons, and that's not good for nitrogen. It cannot expand its octet. right? And therefore, it can actually donate some electrons going somewhere else. And if it can donate something, then it's a base. So that's not good either. Look out for some excess electrons. One way that you can tell if you have an excess electron is that you're negative. So in the case for hydroxide, OH, it's negative because oxygen, let's just draw a bond right there. Oxygen has so many electrons. It's like it has a lot of money and it wants to donate those electron coins because it has so much, right? And it gets a tax reduction in the end. But if you have a lot of electrons and you're negative, that's a really good sign that you're an electron donor. And so that would be a Lewis base, okay? Because it could donate things. All right. So that leaves us with either H3O or BF3. Okay. Let's start off with for BF3. So bromine trifluoride. That's a really wonky bond. Okay. The thing that you need to know is that boron doesn't behave normally, right? It's actually really okay with 3 bonds. And an easy way to remember this is like you have hydrogen, we have lithium, beryllium, if I remember correctly, and like some gaps, and boron, okay? So an easy way to remember boron is you count the rows. That's 1, 2, whatever, 3. This is a really good trick, but only for boron, okay? Since it's in the 3rd column, it's going to have 3 bonds. So that's a really quick, easy way to remember that boron loves to have 3 bonds. So it's okay. It doesn't have any lone electrons, okay? And since we don't have any lone electrons, right, we can actually accept electrons. So let's say element, let's make up a number, not potassium, because just make up something. Element sigma, right, has 2 electrons, or that's alpha, and it goes here. So it's actually accepting some electrons. And so we would have fluorine, bromine, fluorine, and fluorine. And that's pretty happy too. But the main thing that you should know is that boron is really happy with 3 bonds, and it can actually accept the electrons if the opportunity arises. Okay, so that's pretty good. But we have to check out hydronium, which is just a water molecule with an extra H. Okay. So hydronium, let's do this. You have H3. It's a really bad H. H 2 4 6 8 8, and then that would be a positive. So you're probably saying, oh, you know, that's a base because you can deprotonate to do that. Well, is it? Notice something. With the exception of hydroxide, there are no H's here, right? And also, hydronium cannot be a base because I've never seen an HO4, or I've never seen an H4O, right? Have you seen an H4O? I haven't. The max that you can ever have is hydronium. So, if you can, let's say here, I'm going to say, well, the main thing that you should know, okay, the main thing you should know is that Bronston-Lowry acids, right, you can deprotonate to become H2O. Bronston-Lowry acids they are always Lewis acids, right? But a Lewis acid is not always a Bronston-Lowry acid, okay? How can we find an example? Well, this is a Lewis acid. We just confirmed it. But Bronston-Lowry acids have hydrogen, right? They have hydrogen. Does this molecule have hydrogen? No, it doesn't. So it cannot be acting as a Bronston-Lowry acid. Okay? However, this has a hydrogen right here, and it can give away that hydrogen, right? Okay. And since it could give away that hydrogen, it can act as a Lewis acid. So the main thing you should know is that Bronsted Lowry acids equal a Lewis acid. However, a Lewis acid does not equal a Bronsted Lowry acid, as we just seen right here. So because this is a Bronsted Lowry acid, it can act as a Lewis acid as well. And so that's pretty good too. And since we have two answer choices, it would be this one, more than one. Which one of these molecules can act as a carbon-based Lewis acid? Well, Lewis acids tend to be electrophiles. They actually are electrophiles. And phile is love, right? It's love. And love we deem as positive, so that's good. So anything that has a positive sign typically is a Lewis acid. So this would be your answer choice. But let's go into detail on why. Well, we're going to start with methane, which is CH4. Right? Why wouldn't this work as a Lewis acid? Well, again, a Lewis acid loves electrons, so it's going to grab something, right? And you can think of a Lewis acid as a hungry molecule. A hungry molecule is something I call when you want electrons, when you're starving, you don't have enough electrons, right? Well, you don't have enough electrons when your octet is not filled. However, carbon has 2, 4, 6, 8 electrons. So it just went to like Wendy's and got a 4 for 4, right? Deal. So it's full. It's not hungry. It just ate, and it just ate. So if you were to force feed it, it would not like it. It would throw up because that electron, those lone pairs would actually just be hanging out, and you cannot do that because it has a filled octet. So that's not good. Okay. So it cannot be acting as a Lewis acid because we already have a filled electron shell. Lewis acids, they don't have a filled electron shell. They have a gap in it. So this cannot be it. What about HCCl3? Okay. Well, you have a carbon with a hydrogen. You have 3 chlorines. Chlorine. Again, we have 2, 4, 6, 8. We cannot have a lone pair right there. That is not legal, right? Bad. Let's go to CH3 negative. All right. So C and a hydrogen right here in a lone pair. Well, technically it has 8 electrons. 2, 4, 6, 7, 8. Okay. That's 7, 8. Ah, it's yelling. And so it's not going to be acting as that. In fact, it's going to be acting as a what? A nucleophile. Well, hey, what's a nucleophile? Well, a nucleophile is just a fancy way to say a Lewis base, okay? So a nucleophile, these electrons can actually be donated to some molecule, and that molecule would actually give us this, right? And then this would disappear. But can we add electrons? Well, can you? No, because you would have 10 electrons, and that's not good. We're going to be adding electrons. So that's not good for our purposes. So that's incorrect, and that's incorrect. This is a radical. A radical is just where you expect to find a lone pair, you only have 1 electron. And we're going to be covering that, and I think later on in the course. So right now, you should not be thinking about radicals. This is automatically incorrect, okay, because it has 7 electrons. That's pretty weird. So the only thing by deduction is answer choice C. But let's go into it, right? So we have carbon, some hydrogens, and let's see, 2, 4, 6, all right? Whenever you have a plus sign, it means that there's a gap that is positive, right? So 6, or well, let's see, 4 valence electrons minus 0 lone pairs. And then so 4 minus 0 is 4, and then 4 minus 3 bonds is positive. Alright, so it's positive. That means that a molecule can just come up and donate these electrons. Right? It can donate those electrons and give us this. And so because carbon accepted those electrons, it's going to be acting as a Lewis acid. This would be your Lewis base. Lewis base, Lewis acid. You could call that an E file, electrophile, and this is actually called a nucleophile. So let's call that NP, and let's call that EP. Okay. So because carbon can accept the electrons, it's going to be acting as a Lewis acid. The other ones, most of them were filled, and so we cannot accept any acids, or we cannot accept any electrons. We can actually not consider those. Okay. In this reaction, which are your bases? Which species of molecules are your bases? Whenever you do this type of problem, we're going to assume that it's like a Lewis Bronston-Lowry reaction, and it's better to find your acids first. It's better to find your acids first, your acid, and just compare what you have, right? So for cyanic acid, right there, it's actually going to deprotonate, means it's going to strip off a hydrogen and become this, which is just cyanide, if I remember correctly. So because we lost a hydrogen, we're going to be acting as an acid, because Bronston-Lowry acids, they donate hydrogens, right? Okay. So we're not even considering Lewis acids or bases because we're not dealing with electrons. We're technically dealing with hydrogens. So because that was an acid, instinctively this is going to be acting as a base. Okay. And because this was my acid, I know that this is going to be a base. It's actually a conjugate base. And because this was a base, it is now going to be an acid. And so we're going to be looking for our bases, right? So we're just going to say H2O, because that's a base, and cyanide, or something. So these are your bases. So that's a base. That's a base too. Which one is the strongest acid? Right? Well, here's a trend that you need to know for this class. As the pKa rises, our acidity decreases. So it's an inverse relationship. And for bases, as the pKa rises, right, what happens? The acidity increases. Okay? So it's kind of like a proportional relationship. If you were to reverse this as the pKa decreases, acidity increases, and then for bases, as the pKa decreases, acidity decreases. Okay. Therefore, when you're looking for a very good acid, you're looking for a very, very low pKa. And right here, this is a very big pKa, right? And I know that this is a really bad acid. However, it's a great base. So we're going to put a great base right here, or Great Britain. And this is a really big number, so it's also a great base. This is okay. It's kind of like above, it's more basic than water, which is okay. So we're just going to say basic. And when you hit like 10 and below, it becomes pretty acidic. So we're going to say this is acidic, but this is a great acid, okay? A great acid because our pKa is super low. We want the smallest pKa for the greatest acidity, right? So just realize this trend, right? We're going to separate these. Realize that trend. Maybe take a screenshot or something, right? As the pKa increases, the acidity decreases. But when pKa increases, the basicity increases, so the more basic it becomes, right? Whenever pKa decreases, you become more acidic. Whenever pKa decreases, you become a bad base. So it's not a good base, okay? So answer choice E would be your answer. For this question, we're asked what molecule has a pKa of 25? Well, it's good to know your pKa values for this class, but let's say that you forgot to study your pKa values and you're on the exam. Now you're cooked, right? Well, not necessarily, because pKa follows it follows a trend, right? So the trend is that if you have an electronegative atom, oh, by the way, I kind of cut off the molecules because they're pretty lengthy and most of them are the same, aside from the terminal points, which are these molecules that you see. So whenever you have an atom that's electronegative, for instance like oxygen and nitrogen, electronegativity is going to make you more acidic. The more acidic you are, right, the lower the pKa value is, okay? So because I have an oxygen and a nitrogen, I'm going to be in like the low, I'm not sure about the pKa values, but it's like the low 10s at least. So I already know that this is not it, and this is not it either. Now I only have carbons, and man, these are pretty tough because I don't know what to do. Well, what I like to do is I like to draw out the structure. So for instance, we have a carbon triple bonded with a carbon, and that carbon is connected with another carbon, so these have 4 bonds. Okay, this carbon will have an H, an H, and an H. Alright, so you want to be looking at not this part, because this part has another mess, right? You're going to be looking at the terminal point. And here's a trick. When you're dealing with carbons and hydrogens and double bonds and triple bonds, etc., you want to look for the sp trick, the hybridization trick. The hybridization trick is this, okay? So sp, sp2, sp3. The more S character you have, the more acidic you are. Alright? So let's do this. We're going to calculate S character. It's really easy. There are only 2 things here, one S and one P. So if you divide that in half, 50% of this item is going to be 50% S, and the rest is going to be 50% P. You have 3 items right here, so if you divide that in 3, it would be 33% S and 66% P. We have 4 things here. If you divide that in 4, 25% would be S, and then 75 would be P. And so we can see that sp hybridization, it will have a greater acidity, right? It will have a greater acidity. And if, well, I mean, I can lecture you about hybridization too. All right. So what kind of hybridization are we expecting for this carbon? Well, we have 1, 2, 3, and 4 things attached to us. If we have 4 things attached to us, we will have a sp3 hybridization. And since we have an sp3 hybridization, we only have a 25% character of S. And this is not good. 25% character of S, the acidity is gonna, what? Increase over here. So this is gonna be like the most basic. It's like the worst acid. And this is not good. If it's the worst acid, it's gonna be greater than 25 pKa. In fact, this is a single H bond. This is a carbon with single H's, or for instance, this is a carbon molecule that has single bonds. It does not have double bonds attached to the terminal carbon. And whenever you have a single bond, you're expecting a pKa of 50, which is not 50%, but 50, right? Which is really bad for your acid. Okay, if you didn't know what the pKa was, don't worry, because you would know with that trend that the pKa would have to be like really, really high, right? Really high. So not good. What about the carbon? What about this one? Carbon triple bonded with a carbon with an H, right? Okay. Well, what about this? What is that? Well, let's see here. 1, 2, 3, 4 has 4 bonds. That's one thing. That's that's 2 things. So in this molecule, we have 2 things connected to the middle carbon, and since we have 2 things, we have sp, because 1 plus 1 is 2. Okay, we just make the ones invisible. So that's sp, and that means that our S character is going to have 50% S, which is really good. It's really acidic. Now, it's not acidic like, oh, you know, it's negative 50 million. No, it's carbon-based, so it's still a bad acid, but it's going to be the most acidic out of these two. So this is looking pretty good. And if you want me to spoil it for you, it actually has a pKa of 25. Okay, so that's exactly what we're looking for. If you have doubts, just know that a carbon with a triple bond attached to it tends to be sp3 or sp hybridized, and sp hybridized typically is like 25 pK for carbon-based items. And now the next one is going to be CH, so H with a carbon triple bonded with carbon, and oh, did I write that incorrectly? CH2. Oh, that's a double bond. I'm sorry. That's a double bond. That's a double bond right there. Okay. So right here and CH2. Alright, let's check out our hybridization. Alright, so let's see. 1, 2, 3. There are 3 things connected to us, so that's sp2. 1 plus 2 is 3. Okay, so that's sp2. Okay. And that means that our S character would have to be 33% S, which is not okay. I mean, it's not good, but it's okay. It's not going to be the most acidic, right? So the cutoff rate is going to be like pKa of exactly 44, right? So that's not good either. The lowest that you can be for carbon is 25, the highest is like 50, and the 44 is like a medium. So this is going to be sp3, sp2, and then sp. So as you can see, the more S character we have, the more acidic we are. The least S character we have, the more basic we become. Okay, so just follow that trend. And it really depends on what's connected to you at the terminal carbon, not at like some carbon in the middle of the chain. It has to be like the very last carbon at the end of a molecule. All right. So we're gonna skip some problems because I think that they deserve more explanation, and those are going to be at the end of the video. So for instance, well, not for instance, so for now we're just going to be doing like the simple problems, and we're asked to find which one is the strongest acid. So I'm going to assume that you didn't study your pKa, right? Because organic chemistry, I believe, is more than just memorizing stuff. It's actually understanding the concept. So which one is the strongest acid? All right. Well, if you want to do this really quickly, I see that I have 2 molecules that are oxygen-based, and then the other 3 are carbon-based, so I'm just going to eliminate that because I know that carbons are going to just be weak. If you want to know the pK, a triple bond is going to have CH, right? So it's going to be like that. That's 2 things attached to us. That's a sp. sp is like 50, okay, for carbons. For this one, it's carbon double bonded with that. So what is this? 1, 2, and 3. It's sp2. That's like 44, right? Oh, I'm sorry. This is actually not 50. That's actually 25. I'm sorry. And the other one is going to be a carbon with carbons, right? So that's 1, 2, 3, and 4. sp3. It's like the worst one. That's 50. All right. So notice that the carbon-based ones are pretty weak, so they're not going to be good acids. But what about the oxygen-based ones? All right. Well, the oxygen-based ones, let's draw this out. Let's have carbon with some hydrogens. And we will have oxygen double bonded like that. Okay. Well, that's nice. It doesn't tell me anything about pKa. What about the second one? The carbon double bonded with an oxygen, and a hydrogen. Whenever you're doing this type of problem and you want to do it without pKa, just remove a hydrogen. So like deprotonate it, right? Okay. So we're going to deprotonate, which means to remove a hydrogen. And because I removed the hydrogen, I'm going to have an excess negative charge. That's a negative charge. Now we're going to ask ourselves this question. Right? We will ask, which one has resonance? Since they're both electronegative, right? Since they're both electronegative, and assuming that they have like the same amount of like bonds or something, we're going to be looking at resonance, because the more resonance you have, the more acidic you'll be, because resonance, actually, that increases stability. And the more stable you are, the more acidic you'll be. Okay? And therefore, if you're more acidic, you're going to be less basic. Or you're going to be you're going to be less basic, right? So notice that this lone pair, these lone pairs that you have here, 2, 4, 6, 8, 2, 4, 6, 8, it could go here, and then this electron could go over here, right? So it has 2 resonance structures. That's pretty good, right? And therefore it's going to be more stable, it's going to be more acidic. And if you want to know the pKa value, it's around acidic acid's I'd say 4, and then the pKa is going to be, for alcohol, it's 16, right? Because you can think of it this way: liquor, which is an alcohol, it has some water in it, and then water has a pKa of 16. It's really 15.7, but that's the easy way to remember it. So because they have the same bonds, right? Let's put that for whatever. So really, when you're working with these types of problems, you're going to look for bond numbers first, okay? So you're going to be looking for bond numbers first. Let's clear that. So whenever you're deciding acidity, here's the priorities. Priority is going to be bond number. All right. Then after that is going to be electronegativity. And then after electronegativity is going to be resonance. So for instance, we have, like in the previous example, we had carbon with that, then an oxygen, negative. Or something like that. I already forgot. But now, that. Okay, so 3. Let's make that with a carbon. Okay. So, yeah. So let's count out the bonds. Let's see, 1, 2, 3, and 4 bonds. 1, 2, 3, and 4 bonds. So the bond numbers are pretty bad. They're both oxygens, so the electronegativity is pretty bad too. We can't use that, but we can use resonance. And because we can make a resonance structure, we're going to be more acidic, we're going to be more stable, and thus we're going to have a lower pKa value. Alright? In this question, we're asked to find which hydrogen would be the most acidic and which one would be the least acidic. So 1 would be the highest, and then number 5 would be the least acidic, if we're going to rank it. Well, I'll show you what I mean. So we'll rank it A is more acidic than B, and B is more acidic than C, right? So that's what we're going to be doing. Notice that I cut a lot of the molecules out. We're just going to be focusing on the region with the H in it, which is what you're supposed to be doing in the exams, right? So notice that for this type of problem, I'm going to be focusing on electronegativity first, because I know carbon-based things, like if we only have carbons and hydrogens, is going to be really basic. It's not going to have a good acidity level, right? So if I'm looking for the most acidic, I'm going to be looking for like the most electronegative. All right. So I'm going to eliminate 1, 3, and 4 because they have carbons. There's no oxygens or nitrogens. But 2 and 5 have oxygens and nitrogens. All right. Well, since the trend is carbon, nitrogen, oxygen, and fluorine, and we increase electronegativity when we go towards fluorine, and the more electronegative you are, the more acidic you'll become, right? Because of those trends, we can strongly say that number 2 would be correct because oxygen is more electronegative than nitrogen, and both of them are more electronegative than carbon. Since we are more electronegative, we're going to be more acidic. Oxygen just is more acidic than nitrogen because oxygen is more electronegative. So we can strongly say that 2 is going to be our top person, right? So answer choice A, D, and E are out of the question because they don't have 2 in it. And since we're still working with nitrogen, or we're still working with electronegativity, we can say that nitrogen is going to be behind us as well. So 5. And now we can eliminate answer choice C. Wow, so all your answer choices would be eliminated just by doing one trick and not knowing pKa, right? If you want to go into detail about why the others are like these, so for this case, carbon is double bonded, and we know that carbon, when it's double bonded, it's like sp2, which is like, what's the pKa, right? Yeah, since it's double bonded, the pKa is going to be like 44. And then since this is triple bonded, it's going to be linear, so that's sp, which is what? 25. Alright. And number 4, this is all single bonded, so that's sp3, which is like what? 50. And so it should be 3, which is more acidic than 1, which is more acidic than 4. And let's look at the answer choice. We have 2, 5, 3, 1, and 4. And that's why we have our trends. And if you didn't know your pKa, that's fine, because again, the trends are better to memorize. I'm not saying that you shouldn't memorize the pKa. I'm just saying that it helps you out. Like, it makes you more secure about your answer choices, right? So we're asked to find the decreasing order of acidity. Now this is in order of decreasing acidity. Now we know that as acids decrease, the bases increase. So because we're decreasing this way, I know that the most basic one has to be this one, this one, this one, 4, and 5. Because as we go towards the right, our acidity is decreasing. And since acidity decreases, basicity, the basicness, increases. So I should have this as my first person. And the only one that is correct, if you look at that, would be what? D. Okay, and let's double check. So if you were to take out this acid, it would be an OH. And that would be like a C6H5O negative, etc., right? So that would be correct. You always have to make sure what you're doing. So if you feel more comfortable, right, because there's a lot of trick questions on the exam, just deprotonate, take away some hydrogens from this, and just rank them in order, okay? So if it makes you feel better, just take away a hydrogen and then rank the anions in order of decreasing basicity, sorry. So it should be 1, 2, 3, 4, and 5. Going that way, right? So it would be answer choice D. We're asked to find which one would have the strongest base. So if you remember that as the acidity increases, the basicity would decrease, meaning that the lowest pKa would be the greatest acid. But we're looking for basicity, so we're not going to be doing that. This is going to be really strong acid, Still a strong acid. Strong acid. Like anything below 10 is a pretty good acid. However, this is a weak acid. Okay. So if this is a strong acid, then basicity is not good. It's not good for it. Okay? This isn't either. Because as the pKa decreases, the acidity increases. And if acidity increases, basicity decreases. Now, by elimination, this would be your answer. But this is because we have a very high pKa. And a bigger pKa means a bigger basicity. So it's a greater basicity. So you can be more basic, right? And as you can say, as pKa increases, basicity increases, right? So for this problem, we're asked to find which one has the highest, or which one is the strongest acid. Right off the bat, we can eliminate answer choice A because compared to everybody else, this is acetic acid, or that, I'm sorry, that's a carboxylic acid. And carboxylic acids, if you were to remove that, gosh, right? If you were to remove that, then if you were to remove a hydrogen, then you would have what? A C with O, C. That has resonance. Resonance makes it more stable. A stable acid is a more acidic acid. Okay? So oxygen with the carbon and a hydrogen, that doesn't have any resonance. Yeah, they're both the same electronegativity, but they don't have resonance. So this would be the weakest acid out of everybody else. Okay, so we eliminated answer choice A. But what about B, C, D, and E? Well, let's see here. This follows electronegativity trends, okay? So electronegativity, you go from nitrogen, oxygen, fluorine, and right here, Cl and bromine, and we increase this way and that way, okay? Also, if you didn't know about the resonance, well, if you didn't know about the resonance, this is more acidic because it's bigger. So an image I like to use is if you ever traveled in the airport and you have an animal, like a dog, they have to put the animal inside like this box, a kettle. So let's say you have a chihuahua, right? And you put the chihuahua inside a very, very small kettle. It's not going to be good. That chihuahua is not going to be able to move, and it's not going to be happy. And it's going to be all depressed and whatever, not good. However, if you have like a bigger kettle for the chihuahua to move in, it's going to be happy. It's going to be doing backflips, juggling, starting up businesses. You know, very productive, very happy. Kind of like an acid. Acids are typically active, right? They like doing reactions and stuff. And so a bigger, so like the size increases, and so the size increases, the more space the kettle has for the chihuahua, and the more happy the chihuahua will be. So the bigger the size, the bigger the acidity, right? So you can eliminate answer choice A like that if you like that. Okay, well, that's not good. Alright, so let's remove that. Now, we're only on answer choice A, and we're on these two, these three, whatever. Now, this, if you weren't really in class, you would know about the induction effect. So the induction effect is typically when, actually this bromine should be on that carbon. So, bromine, ignore this. Okay, so the induction effect is when an electronegative atom, usually like a halogen is like fluorine, chlorine, bromine, iodine, right? Those are halogens. They exert like a negative force, and that negative force kind of pulls like a rope. So this bromine is a cowboy, and it has his lasso, and he kind of lassos this, and he tugs it. And if you're tugging it, for some reason that makes it more acidic, right? So the induction effect just means that if you have an electronegative atom that's more electronegative than oxygen in this case, it's going to induce a greater acidity because it makes it more stable. It's kind of like oxygen is falling over and then the alcohol is falling over, and so bromine kind of lassos it and lassos him and then pulls back, so we're not falling over anymore. We're actually staying still and we're more stable. Okay, so that's cool. But notice we have two bromines right here, and we're closer to the oxygen and the alcohol. If you're closer to your target, you're gonna lasso him more often, right? And because you can also think of it as a magnet, we're more closer, and so our electronegativity is going to attract us more. And so C would be better than B, right? C would be better than B. But here we go. Here's fluorine. Fluorine is in the same carbon, right? But notice that fluorine is going to be more electronegative than bromine. And so I'd rather have a fluorine cowboy than a bromine cowboy, because that fluorine is more electronegative. He has a more spunk, as you can say, more gusto. And so a fluorine is going to outdo two bromines. It doesn't matter, right? It doesn't matter about that. And we would have two fluorines right here. And you know what? I'd rather have two fluorines than one fluorine, right? And so that's just the induction effect. That one's going to have a greater pull. It's going to stabilize us more. And so this would be the correct answer choice because of induction effect. All right. In this problem, we're asked to find what reactant would give us these products, right? So what reactant would give us these products? Well, I would draw out the answers or the answer choices, but it takes up too much room. So we're going to kind of reverse engineer this, right? We're going to reverse engineer it. Typically, whenever you're doing whenever you're doing reactions, the hydrogen bond is like the first one to go, right? It's like the first one to go. So this bond would give us this nitrogen, right? Or this bond would go to the nitrogen, and we would have H plus and a nitrogen with two lone pairs. And we're just going to blow this image up, right? So I'm just cutting out this portion and showing it to you guys. And let's see here. So that's the H plus, and we have this oxygen. That's negative. Oxygen doesn't like to be negative. It likes to have two bonds. So what am I going to form? Clearly, I'm not going to form a lithium with my oxygen, right? This is because, well, I mean, if we were going to form it, then it would have been bonded already. It's hard to explain, but let's see. You typically see oxygen reacting with hydrogen, yeah? So that hydrogen would actually merge. Actually, I should say this, right? Because we have some lone pairs right here. It's 2, 4, 6, and 8, right? 8. So it's going to bond together. And let's see here, it would be that OH. And it would be bonded with your carbons. Right? Yada yada. Cool. So let's eliminate this right here. Okay. So what would be the formal charge for nitrogen? Let's see, 2, 4, 6, and 8. So 5 minus 4 is 1, and 1 minus 2 is negative, so that's negative. It's negative. Because right here you would have some electrons, right? Because it only has 3 bonds, it wants 8 electrons, so it would have some electrons right there. And don't forget your lithium, right? So that lithium would have seen this gap, right? And because nitrogen likes to have 3 things attached to it, it's going to bond together, and that would give us what? It would actually give us a lithium connected to a nitrogen. Lithium. Okay. But does it work? Does it work? All right. Let's see here. Let's see. Let's see. The first thing that would break off is this hydrogen. So the hydrogen would break off, go here, right? And hydrogen would bond to these. Oh, no, I can't do that from hydrogen. Okay, that's not good. These electrons would bond to hydrogen. And typically we don't like nitrogen with 4 bonds. We always want we always want a lone pair. So this would actually split off. And this would actually split off and give me nitrogen. The nitrogen would have a lone pair, which is pretty iconic, right? We stan. It's pretty nice. Nitrogen always, well, not always, but it typically has a lone pair. All right. And so this lithium would be free and in the wild. And lithium plus, right? So the trick was to realize that hydrogen, if you're going to reverse engineer, that this hydrogen would actually break off and give us some extra electrons, and then it would merge with this oxygen. But the lithium would have merged with the nitrogen as well. If you don't like reverse engineering, you could have just worked it out from the answer choices. I think that's what it was intended for, because answer choice B, you're merging oxygen with lithium and nitrogen, and for some reason there's no H, like the hydrogen just disappeared, so that's not correct. For C, you're neglecting your lithium, and for D, you have an extra hydrogen connected to nitrogen. So where did that hydrogen come from? Not good, right? So your answer choice would be A, right? All right. Thank you for watching. I hope this helps. I hope you do amazing on your exam. Thank you.